here we go. Now, this sounds sort of somewhat embarrassing, but it's true. Dr. Bryant, who teaches Cal 3 class at night, he wanted to take the book home over the weekend, so I'm using the older edition, and I had it marked in the other book what where we left off, and I'm going by this. And you have to remind me, was this the last slide we did, if it ever will come up here, or was this the one we were starting to deal with? Because I don't have my mark here. Had we already done that? Or do you remember? We had done this one. Okay, so we're ready for the next one. So, find that here. Yeah. Got it. Okay. So we were getting ready to start example 3, or had we done example 3? Second? It's evaluate 3x squared sine x cubed dx. We did it. Okay? Had we started example 2, which is evaluate x times x squared plus 9 raised to the 5th power, blah, blah. We haven't done that. Okay. That's where we'll begin today then. Okay. Okay. All right, we'll do it here. All right, before I get going there, let me think where I was. Over the weekend, I tried to get a lot of things caught up. I did get several things, but I was out of town, and we were at a place where the Wi-Fi was DSL, which is really slow. We had a lot of people on it, so it was incredibly slow. So I could not get things loaded there, and then yesterday they decided we had to have contracts due by noon today, so I had to spend all my free time yesterday working on contracts, so I haven't gotten back to uploading things. I'm trying to remember if I got anything uploaded for this class. I think not. I think I was in Cal 1 and had not gotten Cal 2, and I couldn't finish Cal 1. So tomorrow I have 2 hours, office hours in the morning, and then I have sometime in the afternoon. I will try my best to get some of the stuff caught up. I may not get it all done, and then I'll be home this weekend, not the whole weekend, but we have a little bit faster, and maybe I can get it uploaded from home, but maybe not. We'll see. And I'm afraid where I was is where I picked up the virus, because everything since then has been slow. But anyway, we'll pick up and go from here. Since we have 2 new people here, let me go over a couple things. What I was loading to begin with, and what this is doing, is counting how long I've been recording. I record everything on a package called Screencast-O-Matic. It sounds like it slices and dices and cuts. It's not quite that, but it's close to it. And what it does, at the end of class, I upload that to YouTube. Okay? Now that takes a while, but when it finally gets to YouTube, then I put it in the playlist for this class. Well, number one, the playlist is set up, but I don't have the link in Blackboard yet. Hopefully that will get done tomorrow. I hope. If not, possibly some on Friday, though we're going to be out of town most of the day Friday. I may not be able to get it done then either. But I'll try to get it done as soon as possible. So you'll be able to go back and hear everything that we did in class. See, it saves everything that's projected and everything I say in sync, and you'll be able to follow it on YouTube. It doesn't pick up the arm wave, so that won't be there, but everything that's projected, including what I write on the screen like I'm about to do right now. Okay? So here's what we're to evaluate. The and always reverts back to red, and I don't know why. I always change it to dark. Okay. Evaluate x times x squared plus 9 raised to the 5th power dx. Okay. Now, how would you approach this? What would be your first step? Second?
X squared plus 9u.
Okay, very good. My little way I look at it, I pick the most complicated part of the integral, and the innermost part of that, and let that be my variable if it looks like substitution might work. Even if it doesn't, give it a shot. Okay? So that's exactly what he did. He took the most complicated part of the integrand and set the innermost part of that equal to u. So let u equal x squared plus 9. What's your next step? Then du is equal to what? 2x dx. Oh, wait, a big boo hiss. Up to this point, always we found our du to be exactly in the integral. It's not. It's close, but not quite. Okay? This part is being covered by the u. Okay? But all we have is x dx. Down here we have 2x dx. So what we want to do is divide by 2. Okay? Now we have an x dx, and that's equal to du over 2. So here's what I'm going to do. This now becomes, this over 2 we're going to pull on the outside. And then we'll have the integral of x dx. That's du over 2, but we got the 2 on the outside, so that's going to be our du. And what is this part here? X squared plus 9. That's our u raised to the 5th power. All right. I think that maybe even I can do that one. What's the antiderivative of u to the 5th? U to the 6th over 6. Okay? Now, let's deal with the 1/2. That would give us u to the 6th over 12. But this is an indefinite integral, so what else do we need? Plus c. Always when you're integrating an indefinite integral, you have to have some constant of integration there. And sure enough, however, they wrote it 1/12 u6 to the plus c, which is the same thing, 1/12 u to the 6 plus c. And by the way, that's just a very silly, minor illustration of why I don't like the computerized packages, because they're looking for one and only one answer. And if they were looking for this one and you wrote down that one, they would tell you you were wrong. You're not wrong. You just don't have it in the form they wanted. Now, some of these answers we'll get to later have about a dozen ways you can express them. And by the time you go through all those guesses, you probably have already timed out or something. So I find calculus to be maybe not the best thing to use for that. However, those computerized packages do have some pretty good tutorials in them and those kinds of things. So if you want me to try to upload something like that, I can. But if you're happy without it, just doing the homework, that's fine too. Let me know. All right. Got that one done. Let's move on to example 3. This might take a little bit longer, so I'm going to clear all the ink from this slide. Any questions before I clear? Okay. Let's do example 3. Integrate this, why don't you? Okay. X squared plus 2x dx over x cubed plus 3x squared plus 12 to the 6th power. Where would you start on a problem like that? Say again? Okay, start in the denominator. That's the most complicated part of the problem. Usually denominators are. But that one's raised to the 6th power. The numerator is not, and it nearly so complicated. So let's start with that. So what would you let? Let u equal, that's an ugly e, isn't it? X cubed plus 3x squared plus 12. Very good. Next step. Then du is equal to 3x squared plus 6x. Done. Doesn't look like anything in our numerator though, does it? But close. What do you notice? Divide by 3. So let's, oh, and I forgot my dx here. Okay, write it in differential form. Divide both sides by 3, and this becomes x squared plus 2x dx. That now looks just like my numerator, okay? But it's a du divided by 3, and since the 3 is just a constant, let's pull the 1/3 on the outside, and what does this become? The integral of du over u to the 6th power. Now maybe you like to integrate it like that. I don't. I don't ever like to integrate radicals. I don't like to integrate exponents in the denominators. I like to rewrite it as 1/3 integral of u to the -6th du. I like that a lot better because that's a power form. So this will be 1/3 what? U to the oh, what did you say? Fifth. Okay, I thought you said 6. Okay, -5 over -5. Got it. Okay. Now, what that becomes is -1/15 u to the -5 plus c. Don't forget your plus c. Which would then plug in what u is, -1/15. What was your u? Bless you. X cubed plus 3x squared plus 12 to the -5th power plus c. All right. Let's see how they wrote their answers. -1/15, x cubed plus 3x squared plus 12 to the -5th plus some constant c. Why they put capital C's, I don't know. Little c's fine. K's, Fred, I don't care what you put there. Okay. Now, they have a little conceptual insight here. It says an integration method that works for a given function may fail if we change the function even slightly. For instance, if this was a 2.1 there, that doesn't change it much, does it? Except you're never going to get that out of this, okay? It's just not going to happen. So then this very nice system we had doesn't work at all. On that, numerical integration. No way around it, okay? So don't expect them all to come out right. In fact, in real life, you're probably going to use packages most of the time, not real integration. But this is fun, isn't it? So we're going to practice it and do it. Who cares about real life? I mean, okay. Now, example 4 looks like it's not going to, I don't know. Let me erase it just so it won't be so crowded. Anyone need this up a little longer? Okay. Let's do example 4. Going to integrate the sine of 7 theta plus 5 d theta. All right. What would you do with this one? Second? Can't hear. 7 theta plus 5 is going to be your u? Yeah, I like it. Let, and u is fine. If you want to go to another Greek letter, you could use that too. I like you. I like you a lot. Okay, never mind. Let u equal 7 theta plus 5. Then, next step, du is equal to, second, 7 d theta. Okay, 7 d theta. Well, we got a d theta up there with no 7, so what would we better do? Divide both sides by 7. These go out. Now we got a d theta. So this integral will become what? The integral of, let's take the 1/7 on the outside, and then we have a sine u du, because we took the 1/7 on the outside. Okay, I think maybe I can even do this one. This is 1/7. Antiderivative of sine theta d theta. Negative cosine. And it's not theta, it's u. Okay. And we're going to put a plus c in there in a minute. Let's hold off from now. So this is going to be a negative 1/7 cosine of, and what's your u? 7 theta plus 5, and then we can put our plus c. All right, let's see how they did. Negative 1/7 cosine 7 theta plus 5 plus c. Okay. Be sure you use those parentheses, otherwise you might think the plus c is part of what the cosine argument. It's not, it's outside. Okay. I think I have room, but anyone need this a little longer? If not, let's go to example 5. Let's evaluate this one. The integral of e to the minus 9t dt. I can't write very well, but there we go. What would you do here? Let what? Let u equal negative 9t, then du is equal to? Y'all awake yet? Okay, make sure, okay. Negative 9, I can't write. Negative, okay, 9 dt. Very good. But we don't have a negative 9 in there, so let's divide that out. So this becomes negative 1/9. Get that on the outside. The integral of second, e to the u du, right? Because your du, we got the minus 1/9 on the outside, so you're left off with the du instead of dt. And I think we can do that. Negative 1/9. What's the antiderivative of e to the u du? E to the u, my favorite function. Okay? integral and derivative, same. Okay, and then we'll have, well, let's not do it yet. We probably should, but why write extra stuff too soon? Not too soon, but before you need to. Now plug back in minus 1/9. Minus 1/9 e to the negative 9t plus c. Now, that's how they leave it. Sometimes, when you're dealing with exponentials, you can monkey around with the constants and write the constant in an exponential form and sometimes incorporate it in the other part of the exponential. Let's not do that. It just sort of complicates matter. Later, when there's a reason for doing it, we may do it. But right now, that's perfectly fine to leave alone. All right. Good deal. Anyone need that a little longer? No questions? All right. Let's do example 6. How in the world are we going to do this? The integral of tangent theta d theta. I don't think I know an antiderivative for tangent. Excellent. Okay. Anytime you have trig types things going on, you don't know what to do, a good thing to do is get it in terms of sines and cosines. So what will this be? The integral of sine theta over cosine theta d theta. Haven't changed anything except use the trig identity. Now what? What is going to be your u? Huh? Cosine. As I said before, pick the most complicated part of your function. Okay, innermost part of that. There's no innermost here. The denominators are always more complicated than the numerators, so let that be your u. So, let u equal cosine theta. Then, what? du is equal to what? How about negative sine? Okay. Negative sine theta d theta. Right? Okay. This one, integrating and differentiating back and forth, got to keep those signs with the SIG ends right with sines and cosines. Okay? Now, whoa, look at here. Except for the minus sign, we have our numerator, don't we? So let's just factor out a minus 1, which in other words, just change the signs of both sides, okay? That's the easy way to do it, okay? So negative du is equal to sine theta d theta. So our u integral becomes negative integral of du over, I can't write, u. Now, according to one of my last little statements, let's try it. I said something on the order of, I didn't like doing that, so let's make this a minus the integral of u to the minus 1 du. Think that's going to work? Say again? Okay, well, let's see if it does. What would that give us? Minus. Ooh, yes. Oh, something's wrong with this picture, Houston. What's that? A 0 power, and put that 0 in the denominator. We've blown up everything, okay? Not good. So this is the one that doesn't work well with. Because you probably should be remembering, where did that go? The whole thing just disappeared, okay? Let me reproduce it as quickly as I can. What we had, we started with the integral of tan theta d theta. I'm not going to redo it all. And we had let u equal cosine theta and du is equal to minus sine theta d theta. And when we did that, we wound up with the integral minus the integral of du over u. Have I got that right so far? Okay. That's where we were having problems. Don't move that one to the numerator. What we need to do is remember, does that look vaguely suspicious? Log, you're absolutely right. This would be minus the log of, now the trouble with logs is you have to use absolute value of u. Okay? And we're going to put our plus c in a minute, but let's go and substitute back in. So this will be minus the log of absolute value cosine theta. Whoops. Plus c. All right. And now we run into another little thing. This is another example. That is a perfectly correct answer. Is it quite in simplest form? You might argue, yeah, it's fine. But you might also remember that one of the rules for logarithms, if you have an exponent or a coefficient in front of a logarithm, you can move that, exponent. Coefficient in front of a logarithm, you can move that up and make it the logarithm of that as the exponent. So this could be written as log absolute value cosine theta to the minus 1 plus c, which you could also write as log, and that's a perfectly good, legitimate answer, correct answer as well. Or you could write that as 1 over absolute value cosine theta, because that's minus 1, okay, plus c. Well, what is 1 over cosine? Oh, what would that be? Secant. That would be the log of absolute value secant theta plus c. Now, again, any one of those are perfectly correct answers. I'm not saying this is really all that much simpler than that. Sure, you don't have the leading minus sign, but I count cosines a lot simpler than secant. So, to me, I just about as soon have that as I would this. But to lose the minus sign, you get this, and that is, by the way, the same answer. Okay? And when you go to using things like integral tables that you'll find generally at the end of your text, this one's about had it, because this is the old one. If you find your trigonometric forms and the integral of, well, I thought it was going to be here. No, it's not. It's under basic forms. Back of your book, number 11 is integral of tangent u du is log absolute value secant u plus c. Exactly like we got here. So they do count that as the simplest form. Though I would argue that other one up there is just as simple. I prefer cosines to secants. I have a fair confidence level. I know what I'm talking about with them, but secants I have to always, to evaluate a secant, you got to do 1 over cosine in your calculator anyway, because it doesn't have secants. So. Okay. One more. And this one I know is going to take a while, so let's do erase all ink. Evaluate this one. The integral of x times the square root of 5x plus 1 dx. Okay. On first glance, this doesn't look very promising, does it? Second? Rewrite it? How you want to rewrite it? X plus 1 to the 1/2 power? I will always agree with something like that, so let's do that. It just avoids the problem till later, but we'll do that. So that's the integral of x times 5x plus 1 to the 1/2 power dx. Okay? I like that better, yes. But, can you see a real obvious substitution here? If that was 5x squared inside, I'd say, yeah, we can handle that, because x is related to that. But what would be your first inclination? If you didn't look that far ahead, what would you have done? Okay, and what would you substitute? Let u, that's a good choice, equal the innermost part of the most complicated looking part of the integral. What would that be? 5x plus 1. Okay? You buy that? Okay. Now, then, what's your next step? du is equal to 5 dx. We've still got a problem, Houston. That x there doesn't get incorporated into our other. But I'm going to show you a trick. Okay? If a trick works a few times, call it a method. Okay? So we'll do a trick to begin with. Let's take this one and solve for x. And what do we get? Be the first thing you do. Subtract 1. So that would be a u minus 1 is equal to 5x. By that. Now solve for x. Divide by 5. Okay. Now let's see what we got. The integral of x is, that dividing by 5, I'm going to pull it on the outside, 1 over 5. You okay with that? You're not, I can tell. Okay. Okay. And then you have, instead of x, the 1 over 5 is already on the outside, and you have a u minus 1, right? That's what your x is over 5. You still got this one to deal with. We don't have a 5 here, so we need to divide by 5 again here. So I guess that makes this a 1 over 25. Yuck. And this will be, there's my u, right, to the 1/2, right? I'm trying to figure out where to put my parentheses. I think I like it just as well. Yuck. There we go. I think I like it just as well doing it like this. Okay? And then these went away, so that gives you a du. Okay. Have I filed up your mind adequately that you have no idea what we're doing yet? Or is that okay? Huh? It is. But are you agreeing with it so far? All right. I think I got some swampland down in Florida also. No. Okay. All right. Now what can we do with that in a graph? Does the word distribute come to mind? Oh, yeah, we might be able to do that, mightn't we? So let's do a 1 over 25. That's out there. And what would that new integral be? U times u to the 1/2 is u to the 3/2 minus u to the 1/2 du. 1 over 25 still here, don't forget it. Can we do an antiderivative of u to the 3/2? Say again? Yes, okay, good, all right. Binary answer, yes, okay. What would it be? U to the 5/2. 5/2, I wrote 5/5, dumb. 5/2, and what you multiply by or whatever? Dividing by 5/2, which is the same as multiplying by 2/5, right? Minus, how about that next one? U to the 3/2 times 2/3. All right. And then we're going to have a plus c. We could put it now. I'd just as soon wait if I can. All right. Yeah. I think I would be tempted to write this as 2 over 125 u to the 5/2 minus 2 over 75 u to the 3/2, and then I'd put my plus c. Why not? Let's write it down so before I forget it. But let's go back and plug in what u is, or ur, or whatever. What is that? 5x plus 1. So this becomes 2 over 125 5x plus 1 to the 5/2 power minus 2 over 75 times 5x plus 1 to the 3/2 power plus c. Now, there's a big part of me that doesn't really care for those fractions and stuff. So let's factor out a 2 over 25 times, and that will leave 1 over 5 times 5x plus 1 to the 5/2 minus 1/3 5x plus 1 to the 3/2 plus c. Now, to me, that's, and the plus c can go in or out of the parentheses. Since we've been carrying it around out, let's take it out. Yeah. Okay. The eraser's not working. No, it's still not working. There we go. All right. Now, I like that answer as well as any. I'm not sure the book does. Let's see what the book uses. Nope, they left it in the previous one. 2 over 125 times 5x plus 1 to the 5/2 power minus 2/75 times 5x plus 1 to the 3/2 power plus c. Yeah. So they like that form up there. Just such weird fractions. I like these fractions a lot better, and it's just at a common value. again. Both of them perfectly correct answers. That may be a little simpler because you have fewer fractions. Here you have 2, there you have 3. Those 3 simpler fractions and the 2 complex, but whatever. Okay. But they left it in that form. Any questions? So that was a little tricky in that the x doesn't look like it can be dealt with, whereas it really can if you manipulate the u's around there. And that works well because you wind up with a monomial here that you can distribute across the binomial. Can't do it there because that's the square root and that's x. You can't distribute that way. You can distribute this way. So if you can get to a monomial with the fractional exponent, that's a lot better. Trick. Do it a few times, call it a method. Okay. Got it. All right. They called it an additional step is necessary. Okay. Now, we've been dealing with indefinite integrals, okay, using substitution. What we're about to do is what do we do if we have definite integrals? And there's 2 possibilities here. And I'm tempted to say they're equivalent, and in one sense they are. But there's another reality here. If you have definite integrals and you change your variable in that next line here, it's sometimes a really neat thing to go and change the limits to the new variable. Because if you don't put your du here, these are for your x. When you change from x to u, then this looks sort of complicated. In reality, it's pretty easy. You just plug in these x's into your let u equal, and that gives you your u's, and then you integrate it this way. You don't have to come back. If you did it as an indefinite integral and carried it all the way, then you have to get back to your x's and then plug these back in. That's extra steps. Now, I have this little theory about mathematics, okay? It's my contention is to be really good at math, you have to be just a little lazy. Do any of you qualify? Oh, a couple, okay. The rest of you are hard workers, you can still do it. I won't dissuade you. But you see, in math, you're always looking for the easiest way to get the problem done. And I think you'll find this usually is going to be the easier way. You can eliminate a few steps. Do it. And it's actually pretty simple to do. Now this form looks the same as what we did before, except now we have limits, but now we have to deal with the limits there too. You can't use the same limits for x that you had for u. It's just not going to work. So you have to adjust them as well. But I think you'll find once you do it, it'll turn out being pretty nifty. So let's do example 8. Okay? Of course, to do it, I'm going to lose that. Here's our integral. The integral from 0 to 2 of x squared times the square root of x cubed plus 1 dx. All right. Where would you begin? What's that? Okay. So you want the u to be that? Is that what you're saying?
Yes.
That u equal x cubed plus 1. Yeah. Take the innermost part of your most complicated part of your integral. I agree. That's it. Then See, we do this just like before, up to a point. What do you have? du is equal to 3x squared dx. Not exactly what we have there. What do we got to do? Divide out of 3. So we lose that. Now that's looking a lot like that. So what I want to do here, I'm going to write my integral, but at the same time, since I know I'm going to wind up with a du here, I want the limits on this one to represent u, not x's. And where do we do that? Right here. When x is equal to 0, what is u equal to? 1. So this one becomes, the lower limit becomes a 1. When x is equal to 2, what does u become? 9, exactly. So this will be going from to 9. Now, did you think of u of a and u of b? No, that's what you were doing. You just plug them in, okay? You're doing u of a and u of b. Man, just plug it in. It works, okay? Now, oh, we have this 1/3 out front. Don't forget that. We have the du already. That was the x squared dx is 1/3 du. We got that part. Now, I don't want to put it as a radical. I want to put it as an exponent. So this will be u to the 1/2. Ka-ching. What do we do from here? Antiderivative of u to the 1/2 du. 1/3, don't forget that, I almost did. U to the 3/2 times 2/3. But this time we evaluate it from 1 to, yuck! I hate it when it does that. From 1 to 9. Okay? No plus c's required. Okay? You're doing an evaluation on it. All right. Now, the 2/3 is not going to mess with anything, so I'm going to go and pull it out with the 1/3 and make this a 2/9 out front. And then I'm just going to evaluate the u to the 3/2. I'm going to evaluate that plugging in first a 9. Now, what does it mean to raise a 9 to the 3/2 power? Okay, you're cubing with this and taking the square root with that. Now, which you think is easier to do? Who is my lazy one? Okay.
Probably 9 square root of that. Probably easier to cube 9 than to square root of it.
Okay. You're going to do what?
Probably easier to
Cube first. Okay, so he's going to cube 9. Good luck with that. And then take the square root of that. I don't think you're nearly as lazy as you thought you were. Okay?
I'm thinking that 3 now. It's not going to work.
Okay. So it will work.
It'll just be around the world to get there.
Yes. How about taking the square root of 9 and cubing it? What does that give you? Say again? Okay. Cube root of, square root of 9 is 3. We cube that. 27. All right. So this will be 2/9 times 27 minus, okay, when that was a 0 there, I liked it. It's a 1 now, so we actually have to do it. And this one, we can do it either way, okay? I always like to do square root first if it's easy. Square root of 1 is, and 1 cubed is 1. So 1 minus 1. Okay? So this will be 2/9 of 26, which you could write as 52/9. All right. That seems weird, but that's exactly the answer. Good deal. See that? See how we did it? Maybe more important, explicitly why we did it. Did I think about U of A and U of B? It's pretty easy and straightforward. All right. You could have gone the other way and done it, forgot the limits, treated it as if it was a indefinite integral, but before you do the plus c, then plug back in your x, your x's, and then evaluated there. You could have, but it would just been more work. Okay, I think most of the time you find this is a little bit easier. Okay. I think they show a couple graphs with this, and yes, here is, which was that? Yeah, that was the one we just did. Here is actually the graph of that function that you're integrating under. So it's area under this graph from 0 to 2. Okay. Now, when you do the substitution and get it in terms of u's, this is your graph. I guess I could blow this up to make it easier to see. Boom, I blew it up. Okay. Now you're doing the integral under this one, a simpler thing here, from 1 to 9. And sure enough, this area is the same as the other one. Believe it or not, it would be. That's the region represented by that one. Not particularly obvious they'll be the same value, but all the steps along the way took you the same route, so you got there. Any questions on that? Okay. Why not let's throw in a trig one here, okay? Here we have the integral from 0 to pi fourths of tangent cubed theta times, I can't find it there, there it is, secant squared theta d theta. There will be some issues with this. We'll come back and address those later. What do you reckon we ought to do here? Okay, that is a possibility, but let's just take a look at what we get. That would be a sine cubed over cosine cubed divided by cosine squareds. Somehow that upsets my stomach worse than this one does, okay? Anything else we might go by? Say that one more time. Okay, in other words, let u be tangent, is that what you said? I couldn't understand. My hearing is bad. So secant in terms of tangent. In other words, use a Pythagorean identity. That certainly is a legal thing to do, but again, my stomach's sort of rolling on it, okay? What's that again? Okay, I think I see where you're heading on that one. I'd rather go the other way. Say again? Okay, now, again, what was my first rule? Take the most complicated part of your thing and the innermost part of it. That would get you to tangent. Let's just try it. See what happens. This way we luck into it. This isn't the right reasoning for it, but it does work this way. Let, why is my pen not writing? There it goes, okay. U equal tangent theta. Now, I think the next step is going to show how we lucked into it. Then what? du is equal to, oh my goodness, what's the derivative of tangent? Hey, what did you say? Secant squared theta d theta. Oh my goodness, have we been living right or what? Okay. Look at that. And there, no, look at this, okay. All right. There you have your du, and there you have your u cubed. Oh my. Oh my. Okay. So this becomes, whoops. We also got those limits there, don't we? So how do we deal with those? We know we're going to wind up with a du out here, so we need this in terms of u's. What's the tangent of 0? 0. Okay, so the u down here will still be 0. And what's the tangent of pi fourths? 1. Ooh. Somebody likes us. Okay. This isn't looking too bad, is it? And then what do we have? Your integrand now? A little louder? U to the third. I think even I can do that one. What would that be? U to the fourth over 4, evaluated from 0 to 1. And what would that be? One fourth. That's all, folks. That's it. 1/4. Now, what I was kind of hoping you would see is that the base function here, tangent, there's the derivative of it. So that goes right back to our first definition of substitution. When you didn't see that, well, at least just try what we did before. Pick the most complicated, innermost part of the most complicated thing. Well, this is cube, that's squared, do that. And sure enough, it worked out for us. Very nice. Now, wow. Do you think we could have done 0 to 3/4 pi? What's that? Okay. First, I want you to picture that. Picture your tangent function. Okay? Isn't that it? Vertical asymptotes there. These are at pi halves and minus pi halves. Oh, we don't want to do that at all, because that would be taking us from here to somewhere here. And then you'd be crossing an infinite divide. No. That's why they were very nice to us and just went 0 to pi/4. Yeah, we could do that. And negative infinite. The other, yeah. That's not. Okay, to say we did. Okay. So yeah, you don't want to do that. You never want to integrate over something where you have a discontinuity. If you do, break it into pieces. Okay. And you might just luck out and get the right answer anyway, in spite of yourself, but don't bank on it. Okay. So always have a mental picture of what you're doing. 0 to pi/4, yes, we can handle that. Doing the tangent. And by the same token, secant is infinitely, it's like this and like this. So yeah, you have a huge discontinuity there as well. So no, you don't want to do that. This one, they avoided the trap by giving you a good limit. Okay. Let's clear that. Any questions on that before I clear it? Okay. Let's do example 10. calculate the area under the graph of, well, let's see. Let's just go to this. Okay, here is the graph. Calculate the area under the graph of y is equal to x over x squared plus 1 over 1 to 3. And when they say this over was your dividing line, that over means in that interval. Okay. Now, when you're doing integration or area under a curve, I think I will blow this up to begin with, but I'll reduce it down when I have to write. Okay. If you had done an interval, say from -1 to 3, you're going to have some issues there, mostly because integral over here is going to be a negative, and this is going to be positive here, so you're going to be wiping out, and you're really not got the absolute area, you've got the subtracted area. So be careful with that. So it's not a bad idea to do this, but you don't even have to draw it. All you have to do is look at this and say, as long as x is positive, which it is all in this interval, then this is always positive. It's never negative. Because x is positive, and this denominator is certainly positive. So yeah, you'd never have to worry about it going negative without drawing it, okay? But if you had a negative over here, then that goes negative, that stays positive. Yeah, then you'll have negative, so you wanted to avoid that. So for now, we're happy they didn't even want us thinking of it, but it's not a bad idea to think of. Okay? You don't have to draw the picture, they drew it for us, thank you very much. But let's do the integration now. Well, what is area under a curve? An integral. So when it says what is, or calculate the area under the graph of this, that means the integral, all right, until I reduce. Okay, that's the integral of x over x squared plus 1 dx from 1 to 3. Okay? And where would you begin? Okay, let your new variable, we all love you, don't we? We love you, okay, equal to x squared plus 1. Right? Most complicated part quite often will be the denominator, and this one definitely is. Then, what? du is equal to 2x dx. Well, all we have is an x dx, but we can remedy that by just dividing away to 2. Okay? So this will then become, but pause a moment here. What are our new limits? X is going from 1 to 3. What's u going from and to? Say again? 2 to 10, is that what you said? Okay, my hearing's bad. 2 to 10. Perfect. 1 squared plus 1 is 1 plus 1 is 2. Didn't know you'd be doing this high-level math today, did you? Okay. And then 3 would be 9 plus 1 is 10. Got it. And then what's your integrand? Oh, we got that 1/2. Don't forget that. And then what do we have? Second? Yes. 1 over u. du or du over u. However you want to say that. Okay? Second? All right, we got to do a log here, don't we? Okay, so that's going to be 1/2 natural log of u. Now, normally I'd put this with absolute values, but guess what? Dealing only with positive numbers here, so we don't need to worry about absolute values now. So we'll do log u evaluated from 2 to 10, which will be 1/2 of natural log 10 minus natural log of 2. And guess what, folks? There aren't any log rules that are going to make that any better, okay? We're kind of, oh, wait. Let me back off and say, yeah, we can, maybe. Can't we? Let me think about it a minute. That's 1/2. That's, do it this way, log 10 plus log of 2 to the minus 1, so it'd be 1/2. And goodness gracious, my brain hurts. I'm trying to remember if those work. I don't think so. Does it? No, we leave it just like we had it. Except, I wrote it this way, they wrote it that way. If you want to actually figure out what it is, you, they left it like this. Plug in values and get an approximate answer. If you got a calculator, do it. Probably easier to do that one than this one, but whatever. 1/2 of log 10 approximately. Maybe around 3-ish or so. 3 point something. Minus log 2. Log 2 is going to be less than 1, so I don't know. Then you're going to take half of the answer. The book gives them as approximately 0.805. You don't have to give an approximate answer. That would be perfectly all right to leave as it was. They multiplied that 1/2 through. I don't care. But that sounds about right. Because if log 10 is on the order of 3 or so, then half of that would be an order of 1/2. Log 2 is a decimal number, and half of that would still be a decimal number, and subtract that from, I'll buy it. I can't think of anything else. Okay, finish 5-6. Now the instructor here who chose this book as the book we use, though I have a lot of issues with it, she loved having the summary at the end of each section. And that was the main reason she chose it. So it does have 4 major bullets there. If you know those, you got the section down. What I've grown to like pretty much is these preliminary questions at the end. I don't know if you like them or not, but let's deal with them just to see if you think they're worthwhile or not. Which of the following integrals, I do like this one, is a candidate for the substitution method? I'm going to write down all 3. Okay? The first one here is the integral of 5x to the 4th times the sine of x to the 5th dx. The B one here is the integral of sine to the 5th x dx times cosine. Ooh, I messed that one up. Let me... Well, it didn't take. There it did. Cosine x dx, and c here is the integral of x to the 5th sine x dx. Okay. Which of these 3 integrals is a candidate for the substitution method? And you may have 0, 1, 2, or 3 of them. but which of these do you think might be? Second?
Instinctively, I have to say
B definitely is, because the derivative of sine is cosine. Yeah, that will give you that. But guess what? A works too, because the innermost function there be your x to the fifth, derivative of x, 5x to the fourth. Yeah, that's going to work quite nicely. How about C? Hang it up, Jack. I did. I'm trying to think what my, oh yeah, I know what works. Something we haven't gotten to yet. We'll hit 2 chapters. No, 1. Yeah, 2 chapters. We'll hit exactly the way to do that. So, no. A and B for sure. C, not for sure. Okay, definitely not. Okay. I like to always check the back and make sure I haven't missed something. All these are in the back. This is 5.6 preliminary question. A and B, good for them. Okay. Number 2, find an appropriate choice of U for evaluating the following integrals by substitution. Okay, again, we got 3 of them. The first one of these will be the integral of x times x squared plus 9 to the 4th power dx. The B one here is going to be the integral of x squared times the sine of x cubed dx. And the C one here is going to be the integral of sine x times cosine squared x dx. Okay? All they're asking for is you pick the U. What you want the U to be in A. Say again? I think you said it right. I don't hear well though. X squared plus 9. Good for you. Next one. Let U equal x cubed. Good. And then the third one, let U equal cosine x. All right, I like all 3 of those. Let's see if the back of the book likes all 3 of those. 5, 6. A is x squared plus 9, B is x cubed, and C is cosine x. Good for them. Okay. Number 3. Let's erase. Any of you need that up longer? Okay. Do any of you have books yet? You don't? Okay. All right. Number 3. Which of the following is equal to this for a suitable substitution? So here's what you start with. Integral from 0 to 2 of x squared times x cubed plus 1 dx. That's what you're going to start with. And which one of these is what you get after a substitution? 1/3 the integral from 0 to 2 of u du. The B is the integral from 0 to 9 of u du. And the C one would be 1/3 the integral from 1 to 9 of u du. So they're all convinced that u du is going to be the integrand. The question is, which one of those limits and or coefficients, the coefficients with the limits, which one of those would be the one you would use? C, for sure. The problem with A, you didn't change. You had the same limits for your x as you did for u. No way that's going to be happening. Okay, so that one's out. This one, you change your limits, incorrectly, but you changed your limits, or you changed one of them anyway, and but you had nothing to do. You had no way of getting rid of the extra 3 there, so that could be it. C, you got the 1/3, that came from the 3x squared, du dx, and your limits got changed correctly. So yeah, okay. Let's make sure the back of the book got it right. And 3 is C. Good deal. Homework exercises here. I think I told you before you could do any of the odds 1 through 5, and I hope you did. Then you can do any of the odds 7 through 21. There's a whole passel of those. Then you can do either 23 or 25, or both if you choose. And then another passel and a half here. This will be 27 to 71, any of those odds. And some of those can get a little on the complicated side, so I would not just do the easiest, do some of the others. Try to do 73. That's a pretty good problem. All right, let me say 73 or 75 or 77. So any of the odds 73 to 77. And then any of the odds 79 to 89. And then 91 or 93 or both. And 95, do 95, and try to do 97. Okay. Now, back up just a little bit. I don't know all of your majors, but problem number 93 is talking about a wind engineer, which I would take it would probably be somewhere either mechanical or electrical or some combination of both. I have found that wind speed in meters per second at a given location follows a Rayleigh or Raleigh, I think it's pronounced Rayleigh distribution, and they give that distribution here. Now that's sort of a statistical kind of a problem, so and you will run into those in engineering. I'm assuming most of you are engineers. So if some of you either wanted to write on who in the world was Rayleigh, or how did he develop this distribution, or applications, where does it fit and where does it not fit, what limitations, you could find a couple or 3 paper topics right there in that one. Any of the other could lead you to something, but anytime I see someone's name, I think, oh, that could be a paper topic. And then those at the bottom, the further insights and challenges, I don't see anything particularly that reaches out and grabs me at those either. Now, since some of you, most of you, seem like you don't have your books yet, if you want to come up and take pictures of these problems so you can work on them, you're certainly welcome to do so. Now, this almost doesn't seem fair, but they did it to you this way. Let me get out. Oh, were there any questions on 5.6, substitution? Okay. Okay. I'll move on to 5.7. Now, in the new text, none of you seem to have it. I think this is 5.8. Okay, but in the old text, which is the old slide set here, and for some reason it's so slow opening. How are we doing on time? We go till 1:40, so we got ways to go. Well, it's just sitting here. It's blinking a little bit, but it doesn't seem to be doing much. Like I said, oh, there it goes. We're losing people. Do y'all need to take a break? This is not a bad time for a break if you need one. I see someone just did, but if the rest of you do, it wouldn't be bad. Ready to carry on? Okay. It looked like it was going to PowerPoint would take long enough to load that it'd be time for all of us to go. Here we go. All right. This doesn't seem fair at all. Now they decided, well, let's show them something about these transcendental functions, especially since we've already had them doing problems with them. Okay, so this is just a reminder. Now this is incorporating what we just did, but tying it in with the fundamental theorem of calculus, part 1, I believe it is, that if you put, if log t would be the integral, leaving the limits of the integral dt over t, that would be log t. If we put a limit here, a 1 down here, and an x up there, that then is the definition for what log x is. Because when t is equal to 1, this is going to basically not give you any, well, when x is equal to 1, you get 0. So log of x is 0. I mean, log of 1 is 0. Okay? So that certainly works, and it works for all beyond that as well. This is for all x's greater than 0. Even x's between 0 and 1. Because if x is less than 1, but greater than 0, then you have the, say, 1/2 up here, 1 down here. That would be minus, if you flip them over, it would give you a negative number, and log between 0 and 1 is negative. 0 at 1, and then positive from there on. So sure enough, this does look like it, and it does work. That's one definition of a log function. Okay? Now the graph to go along with it would be this one. This is your y is equal to 1 over t, first quadrant here. It also would extend here, but that doesn't pertain if you deal with the log, because that would be a negative area. We're not doing that. Okay, so the area under here is log x. Okay? Anytime x is to the right here. If x was to the left of 1, then it would be the negative of this area, because you'd be doing 1 to this, you would be going backwards, and that would be a negative area. But sure enough, that would be a negative number. Okay? So this works for all values x greater than 0. Can't take the log of 0 or anything less than 0. Okay. Okay. Trying to think of how many of these we really want to do. Most of the time, you're going to look these up in tables. That certainly is one that we run into. The next ones they talk about here is inverse sines. Okay, and this certainly is correct, but frankly, do I suggest that you sit and memorize these things? I hate memorizing. So no, I don't do it. If I ever need this, I'll look it up in a table. Okay? But this is what we would have. This is the definition for the inverse sine, which is a transcendental function. That's what the title of this is, for the transcendental functions. Now, this only works for x's between -1 and 1. Well, that sort of makes sense because our inverse sine function is only defined between x's from -1 to 1. Okay? Now, it's actually defined at -1 and at +1, but the integral is not, because if x were either -1 or +1, I'm sorry, in a sense, t were that, okay, then this would be a 0 in the denominator. You don't want to do that. Okay, so that's why they leave off the equal sign there. And again, this is not something I bother memorizing. I mean, if I need it, I'll look it up. Okay. Now, that then leads to, okay, this is the function 1 over the square root of 1 minus x squared. Rather strange looking function, but definitely what it is. And the area under this from 0 to x would be that area. And that's the value of inverse sine x. Okay? It can't go 2, 1 because then you're under an infinite part of the value. But anything less than 1 is greater than minus 1 will work. Okay. And again, not something I find really all that worthwhile memorizing. Okay. But just so you'll recognize what they look like, so if you ever run into them, you'll know where to look, and that's sometimes as important as knowing what the answer is where to look to find them. Derivative of, and you would think this would have been back in Cal 1 when they did the transcendentals, and it probably was. Okay? Derivative of inverse sine is this. Derivative of inverse. Oh, they're not doing cosine. Okay. It just becomes a negative of this. But so therefore, the integral of this would give you inverse sine plus a constant. Remember, indefinite integrals always you have to have a plus constant. Because derivative of inverse tangent is that, the integral of this is going to be an inverse tangent. Derivative of inverse secant is this, strange but true. So anytime you have a form like that, that's going to be an inverse secant. Again, I wouldn't worry with memorizing these. I just look them up when you need them. They're in tables everywhere. And I'm probably not going to memorize it anyway. Now, to get, if you had plugged in inverse cosine here, that's just a negative here. Inverse cotangent here would be a negative here, and inverse cosecant here would be a negative there. So if you had a minus inside any of those, you just change that to cosine, cotangent, or cosecant. Again, look it up. I don't bother memorizing that. Okay. I'm not even sure, well, let's do I was going to say let's not even mess with any of these examples, but just to show you what to do if you run into them, I guess. Here's the first one. Evaluate this integral. I've got to get my pen back to dark again. The integral from 0 to 1 of dx over x squared plus 1. And this is the main reason I'm doing this. What would be your first inclination? Yeah, you would say, can I substitute this? And what would your answer be? No, I can't. Okay? So therefore, you have to look this up somewhere. Now, if you think back to those three that we did, inverse sine, inverse tangent, and inverse secant. Okay? Remember, the tangent had the sine had a radical in the denominator that's 1 minus something another. And the secant has a radical in the denominator, but also had an absolute value in front, a radical, and then you had something squared minus 1, I believe it was. But the tangent looked like this. So this would be a prime candidate to consider an inverse tangent. Okay? Frankly, because substitution doesn't work. Okay? Now, I say that. And I'm going to bite my tongue, because when we get into chapter 7, we'll come right back. I just had it and lost it. Okay, get it back again. We're going to do some trigonometric integrals. Okay? That's not the ones I'm looking for. It's trigonometric substitutions. Okay? And when we get to that, we will see how to use trig situations to actually get these without having to memorize a table. So that's why I think I'm all in favor of let's hang on to this and not do anything with this yet. Okay? Because when we get to chapter 7, we will come up with a technique for this. Okay? But that looks just like an inverse tangent. That's where we would wind up. But I won't show you how we wind up that yet. I do want to do the next one without having done that one. The integral from 1 over root 2 to 1 of dx over x times the square root of 4x squared minus 1. Now, I hope you see a normal substitution isn't going to do you any good here. Okay? If this x were up in the numerator, yes, that would be perfectly hunky-dory. It's not. It's down in the denominator. It's going to be miserable. Unless you remember that kind of looks like secant, inverse secant. Remember the inverse secant, the standard form has absolute value in front of this. Okay? Why you don't need one here, your limits are all positive. So you don't need an absolute value, the x never goes negative. Okay? But this doesn't quite look true because you didn't have a coefficient in that. So here you do a substitution to let u be 4x squared, and then you continue on with that. That's going to change what this is. It's just going to change it by a factor, and that's all. So later we'll get to do these two, so don't sweat those yet. Okay? And then the same with this one. The integral from 0 to 3/4 of dx over the square root of 9 minus 16x squared. Okay. Again, one of our standard substitution, not going to handle it because you don't have an x up here. You would need one to do a derivative of this. But, and it doesn't look like an inverse sine, but it looks similar to it. Inverse sines usually have a 1 minus x squared or something like that. So what you have to do is do a substitution with this to get you into a form that you could use the other. And I think what you do here is divide, just as you do here, divide, under the radical, divide this by 9, which would then be multiplying by 3, right? Because if you divide by square root of 9 and multiply by 3, you get the same thing. So you get a 3 out here, and then you get a 1 here, minus, and you get 4/3 x squared, and then you can do a substitution there. Okay, but again, to use the inverse substitutions, or inverse sine functions and inverse trig function, inverse tangent, inverse secant, inverse sine, you just got to do a lot of manipulating around and stuff. Later we'll see how to work these more directly. So that's all I'm going to say about that for now. And I'll try to remember not to test you on those, since we sort of skipped over it. But I did want to hit one other, and that's this one. This is integrating an exponential function. This is not a power function. A power function has the variable as the base and some number as the exponent. Okay? Number could be a fraction, it could be a positive, negative, it could be anything. But you have the variable as your base and the number as the exponent. This has a number of the base and the variable is your exponent. That is a power function, and you're integrating a power function. Okay? And this is the it may not be intuitively obvious how they went about getting that. Okay? And let me show you basically how they got there. Okay? Maybe I should have done it before I put the slide up. So I'm going to have to lose the blow up here. Here is the observation. How can we take the derivative of a base raised to a power? Okay? That's an exponential function, but it's not with e. Okay? Okay, here's something that doesn't work. It's not x times b, x times b to the x minus 1. No, that works for a power function. It doesn't work for this. Okay? In reality, what we really do is do a substitution. Okay? Now this is taking a derivative. It's not an integral. But what's our substitution? Let's rewrite this. You want to go back to u? Okay, why not? Let u equal I was going to do it that way. I think it's easier this way. Let's just rewrite this as e to the b to the x. No, did it backwards. I won't take a log. Okay, sorry about this. Let's go back to what I was going to do again. Let u equal b to the x. Then, I'm not going to take a derivative. I want to just do something else. Let's take the log of u, and that would be the log of b to the x. Okay? Because that was an exponential function, let's take the log. Then, log u is equal to, now we can use that rule of logarithms. Remember what it was? We've used it once before, either last time or today. Remember how that went? He did it in reverse. That's the same as x times the log of b. Okay? You remember that? If you have a log of something raised to a power, you can bring the power on the outside and this is the log of b. Okay? Now, okay? Now, seems like we're going in circles, but don't get dizzy, we're going to do it. Then, let's take the exponential of both sides. E to the log u is equal to e to the x log b. Okay? Now, e and logs are inverse functions of each other, right? So this gets us right back down to u. Okay? And this u is equal to e to the x log b. Well, u was also this, so b to the x is the same as e to the x log b. Okay. Now let's take that one and take d by dx of e to the x log b. Now, I like taking derivatives of e functions a lot better than I do p functions, whatever they are, right? What's the derivative of an exponential function? Itself, okay? So that's going to be e to the x log b. But then you got a chain rule issue here, times the derivative of the exponent. What's the derivative of the exponent? Remember, b is a constant. So log b is a constant. So this is some constant times x. What's the derivative? It's just log b. You got it. Okay? So let's see what we've got here. D by dx of b to the x is equal to, I'm going to put the log b in front, log b times this e to the x log b is bx times b to the x. Okay? So, they put the log b in parentheses, then b to the x. Doesn't matter. That's what we get. Now, with that in mind, let's divide both sides of this by log b. And that's just a constant, right? Okay. So, what we've got now is b to the x is equal to 1 over log b times d by dx. Okay, it must have decided that I needed to go. It just decided to end. Let's see what happens if I put. What's that? Do what? Keep?
Probably going to do keep and then reload the slideshow.
Yeah, but I think when I try to keep it, it's going to try to write it onto the CD I got it off of, and that's not writable. It's read only. So I don't think it's going to work.
I might just save it around.
Yeah. What I think I'm going to do is go on a discharge. Okay? And let's go back to the very last slide, because that's where we were. Well, let's see what we got here from current slide. Let's see where we are. No. That's what I was afraid of. Oops. Now, okay. So let's, all right, what I just said. B to the x is equal to 1 over log b, d by dx of b to the x. Looks rather strange, but it's true, okay? And because that's just a constant, we can bring that inside, and that would be d by dx of b to the x over log b. Okay. What's that? It really wants to go home. It's tired. Okay. Yeah. What's that?
I think you can right click on the slides and tell it to freeze on that slide and not advance.
Right click on it?
I think you can do that. You used to do it in the older version.
Yeah. I just don't know if it does with my pen or not. I don't know, but let's see. Now, the question is, so what? Okay, maybe. What if we were to integrate both sides of this? Integrate this and integrate this. Well, here we have an integral of a derivative. So this would tell you that the integral of b to the x dx is equal to the integral in this wipe out b to the x over log b, but then with some constant c, and that's exactly where you get that. Oh joy. Okay, just what I woke up this morning saying, how do I do that? You know, no. Let's see if we can put it to use. And again, we'll do it now, but guess what? If you ever have to do this, look it up in a table and you'll find it. So let's clear this slide and see if we can put it to use. Evaluate this. The integral from 3 to 5 of 7 to the x dx. Okay? All right. Now it looks a lot like what we have here, except this is indefinite, that's definite, so we don't have to worry about a plus c here. And what does that tell you we'll have? 7 to the x over the natural log of 7. Evaluated between 3 and 5. So that would be 1 over log 7. I'm just going to take that out. And then this would be 7 to the 5th minus 7 to the 3rd. Okay? Now, pull out your handy dandy calculators, see what 7 to the 5th is, subtract from it 7 to the 3rd. Almost do that one in my head, but not quite. And divide it by log 7. And you'll get an approximate answer. Pretty hefty number, by the way. Yeah. Divide the difference by log 7. And what do you get? Did you punch it in and see? Say again? 8,460.8. Yeah, that's what we got in the book. Good for you. Good for them. How about example 5? Do I really want to do this one? Okay. It really isn't as bad as it seems, I hope. Anyway. Oh, and that's approximately equal to 8405. Let's say, no, 8460. 8460.8. That's what they got in the book. I'll take your word for it. Say, let me erase this so we can go to example 5, because it might take a little more All right. The integral of 0 to pi halves. Smells like a trig function coming up. Sure enough it is. Cosine theta times 10 raised to the sine theta. D theta. Oh boy. How would you proceed here? Toss it out the window. No, that's not an option. Substitute! The words I love to hear. What you reckon it's going to be? Let, why not u, equal what? Sine theta, the most complicated, the innermost part of the most complicated looking part of that problem, integrand, that would be your sine theta. Okay, then du is equal to cosine theta d theta. I love it because there it is right there. All right, so this becomes the integral, but we got to change our limits to du. So when theta is equal to 0, these are the limits on theta, what's the sign of 0? 0. Okay, and sine of pi halves is 1. Right? Okay. Our d theta, our du is cosine theta d theta, so that's already taken care of. This becomes 10 to the u. Okay? And I think that's just below, isn't it? What would that be? Ten to the u over natural log of 10 evaluated from 0 to 1. About to make a guess even I can do that. 1 over log 10. That's going to be the hardest part of this problem, I think. Times second, 10 to the first minus 10 to the 0. Very good. Now tell me what that is. 1 over log 10 times 10 minus 1. I agree with that, and that's going to be 9. 1 over log 10 times 9. Okay? So this is 9 over log 10. And like I said, the hardest thing to do here is figure out what log 10 is. Pull out your handy dandy calculator and see what it is. It's around 3-ish or so. So 9 divided by something less than 3 is greater than 3. Anyone got it? 3.91, is that what you said? Yeah. Oh, natural log of 10 is 2.302. Right. Okay. Divide that into 9 and you get something on the order of 3.91. That's what the book said anyway. All right. Good deal. They have a little summary here, and you can do whatever you want to with that. 3 bullets there. I think these preliminary questions may be worth looking at, so let's erase our ink here and do find B such that, see how we're doing now, we're all right. Find B such that the integral from 1 to b of dx over x is equal to first log 3. Now, if you had your books, I'd say look across the page. You don't have your book, so you don't have a page to look across. But if you remember from way back at the beginning of this section, which is what? A few slides. That's it right there. The integral from 1 to x of dt over t is log x. Okay? And what they're asking us for here is the integral from 1 to b of dx over x, for that to be log 3. What is the value for b? Think of it this way. This is the derivative of this. Natural log of x, right? So the natural log of x evaluated from 1 to b, we want that to be 3. So that's going to be log b minus log 1. What's log 1? 0. So then we have log b equal log 3. What does b got to be? 3. All right, good. That. All right. What about if this thing is equal to 3? What has your b got to be in that case? Our derivative of this is natural log of x. Okay? And you know that 1 is going to be a 0. So we want log of b to equal to 3. Right? Log b equals 3. So what's b got to be? How do you undo a log? Exponentiate. And e log b is b, right, is equal to e cubed. That's what it is. Okay? So you'll buy my answer. A, b is equal to 3. B is equal to e to the 3. Good deal. Number 2. Find b such that, do I want to do this one? I think so. Let's see if we can. The integral from 0 to b of dx over 1 plus x squared is equal to pi thirds. Pretty ugly pi. But okay. Find the b to make that true. Said we weren't going to do these, but I'm hoping you'll remember that much. What does that integral look like? So again? Inverse tangent. Bingo. Oh, can't say that. Okay. Okay. Inverse tangent of something. Okay. Inverse tangent of x. That's what that is. Evaluated from 3 to, that's a b. From 0 to b is equal to pi thirds. Now, inverse tangent of 0 is 0. So we don't have to worry about that. So inverse tangent of b is equal to pi thirds. Is that what we got? You agree with that statement? Inverse tangent of b is equal to pi thirds. Now, can you write that same equation without an inverse trig function in it? What's an equivalent equation to that? How do you undo an inverse tangent? So, yeah, do a tangent. Okay? So do a tangent of this and do a tangent of that. Okay? And tangent of inverse tangent is just going to leave you with the b. One undoes the other. That's why I call it inverse. And this will be, what is tangent of pi thirds? Say again? Okay. Square root of 3? I believe you're right. Let me think just a minute. Pi thirds is that. Root 3 over, yeah. I believe you're right. Square root of 3. Let's see if they think you're right. Square root of 3. Excellent. All right. Number 3. I think I'll clean the page. All right, to clean it. Which integral should be evaluated using substitution? We've seen some of these before, haven't we? Integral of 9 dx over 1 plus x squared, or b, the integral of dx over 1 plus 9x squared. Okay? Which integral should be evaluated using a substitution? B. The first one, just pull the 9 outside, and that's the inverse tangent right there. So you don't need substitution. That one you do, let u be 9x squared, and go from there. Yeah. Okay. Good deal. And let's make sure they've got it right. B, good for them. And then number 4. Which relation between x and u yields this? The square root of 16 plus x squared is equal to 4 times the square root of 1 plus u squared. Again, doing the substitution. Which relation between x and u yields that to be the case? It's going to be something like this. Let u equal something to do with x, right? Now, my gut feeling would be either x over 4 or 4x. Would you think one of those has to be it? Which one you want to try? If it doesn't work, we'll try the other one. And if neither work, we'll figure something from there. Radical 4 over x? Is that what you say? What's that? Okay. I was going to suggest either 4x or x over 4. Let's try one of those first. Say again?
4 over x seems like it work better to me.
Okay, let's try 4 over x then. Let's see what we got. Next step is going, okay. So let's plug this in here. and this would be 4 times the square root of 1 plus 16 over x squared. Right? And then let's pull the 4 into the radical, and that would be the square root of, that would be square root of 16. So that would be 16 plus, not quite where we want it to be. Yeah. Well, let's try x over 4 and see what happens. May not work, but let's try it. Okay? That didn't work. There we go. Okay. X over 4. Okay? So, what we have here is 4 times the square root of 1 plus x over, that would be x squared over 16. Would you buy that? Okay? Now this is the same as the square root of 16 times the square root of 1 plus x squared over 16. Would you buy that? Okay? Square root of 4, 16 is 4. So let's multiply that through. That would be the square root of 16 plus x squared. Yep, that's it. That would be the relationship. Right? Okay. I sure hope that's what they meant by their question. Yeah, x, they said x equal 4u. We said u equal x over 4. Same thing. Okay. Here are the exercises. I would definitely do 1, 3, definitely do any of the odds 1 through 3, and then try 7 or 9 just to see if you got that down. Okay? And then they tell you what substitution to use in 11, and I think you'll find that works well. Later we'll see why they give you that. Okay? So I don't want to waste too much time on it now, but any of the odds then, 13, well, let me just tell you the ones. I would do 13, no, I'm sorry. The rest of these are all trig type, the trig type thing. So I'll let you determine if you want to do any of the odds 13 through 21. You can do them, but I'll leave them up to you. Okay. I think you can do, however, any of the odds 23, and any of the odds 27 through 31. Okay? My eyes are having trouble focusing now. Okay, then in the next group, any of the odds, and this mixes all sorts of things together. 33, 35, 37, 39, 41. I think you can do 43. I'll leave it up to you whether you want to try 45 or not. 47, 49. I think you can do 51. 53. I'll let you decide whether you want to try 55 or not. 57. 59. 61. I'll say any of the odds then. Picking up from 55, I'll let you decide. any of the odds 57 through 69. Some of those could be quite fun, okay? And then 71's a pretty fun problem to do, and 73 if you choose. Okay. Now, 5.8 deals with exponential growth and decay, which is good stuff to be familiar with. I don't know, are any of you going into nuclear engineering or might possibly head that way? Nuclear medicine? Okay. So what I think I'm going to say here, I'm going to, well, let's see. Here's what I meant to do. Okay. Okay. I'll finally get it right. Discharge. Discard. Just for the fun of it, because it's all fun, I'm going to give you a quick slideshow of this, so if you ever need it, you can go back and pick it up if you want to. Not going to be responsible. I'll try not to ask you anything on a test on this. Well, let's see, I have covered it before in the past, so I think I'll just do the slideshow and let it go at that. This is taking forever to load. I clicked on it and it doesn't even change color. Click again. See, nothing's happening. There, that time something happened.
Maybe it's loading from an optical drive.
What's that?
Maybe it's loading from an optical drive. It just takes a while to read it.
Sure is taking its time. Most of the time they just pop open.
That's also 10 times the size of the file you opened previously.
What's that?
The file.
Oh, it's a pretty big one.
Yeah, it's a pretty big file.
Still, they don't take this long to open.
Yeah.
Now we're going to go through all this again. I love PowerPoint. My favorite. In fact, I love everything Microsoft. Not. Okay, but everything is Microsoft, so you have to use it.
Let's go and pay an extra $1,000 for the same hardware with Mac.
What's that?
Let's go and pay an extra $1,000 for the same hardware with Mac.
Oh. All right, let's go with current slide. And all I'm going to do here is do the slideshow pretty much and do, for me, minimum talking, still too much talking. This is basically what, this is some quantity. This could be a population. This could be growing bacteria or something like that. Population at any time t would be your initial population, e to the kt, okay? Where k is kind of like the growth constant, okay? If this is exponential growth, that has to do with that. Now, I don't know if y'all mess much with exponentials. I know you've done some, but just to give you kind of a feel for it, what exponential growth is not linear growth. In time, you go up the same amount every time period. And it's not a power function either. Okay, that goes up pretty fast. But exponential growth is going up by factors. Okay. And here's a sort of a dumb example that let's just take. If I say, picture a pickle jar, what do you think of? A quart jar that contains pickles or something like that? Well, my mom used to put up pickles. We'd harvest the cucumbers. We grew up on a farm, and get the cucumbers, and then she'd soak them in salt water for a long period of time, and I think some lime in it and some other stuff that made it crisp and stuff. She had a big, it's about a 3-gallon jar, and it was clear, and she do the pickles, lay them down, make sure they all stay down there. In the brine, it's salt and vinegar for a long time, several days, weeks, something like that. So picture this pickle jar, okay? Now, I'm initially going to put a single bacterium in there, but it's going to be in a perfect growth medium for bacteria. This particular bacteria, it loves this stuff. So it's going to be able to consume the growth material and start multiplying, of course, dividing. Okay, now, I want you to tell me what the dividing period should be. You can pick so many days, so many hours, so many seconds, so many weeks. You just give me some time period. We're going to say it's going to take that long for this to double in size. An hour. Okay, 1 hour is doubling period. Okay, now when do you think the jar is going to be full? You can make up something. A week, a month, a day, 17 hours. I don't care. Make up time. If you think it's going to be full. Certainly going to be more than an hour because it's probably going to double in an hour. So sometime out in the future. Name it. 3 days or 72 hours is what you said. Okay. That's when it's going to be full. When is that pickling jar going to be half full of the bacteria? Second?
Oh, it's going to be half full. That's 71 hours.
Yes, 71 hours. Not a day and a half, or it's going to be 1 hour short of when it's full. It's going to double every time period. Okay. That's what exponential growth is about. I mean, when it gets going, it gets going. Now, why do I ask that? In some of my science classes, physical science, and other things, our appetite, when I say our, U.S. appetite for energy, is pretty close to being exponential. Okay, we're not down to the linear, even of power function. We are doubling our energy. Now we slowed the period. Okay, what may have used to been a few years, now we've made stretch it to 20 years and stuff, but it's still exponential growth. At some point, fossil fuels have got to run out. I mean, they're not enough. If you think about what fossil fuels is, they're things that have been developed over tens of thousands of years to produce this coal, or the natural gas, or petroleum, or whatever. So it's taken a long time to make those, and we're using them just as fast as we can find them. Okay? So at some point, we're going to be used them up, right? When will we know that? We probably will, when we get awfully close to it, we're probably going to be within one doubling period by the time we figure that out. So we're going to have very little time left to come up with solutions. So we need to be thinking of solutions now. Not when it looks like, oh, yeah, we're getting close to the end. When we're close to the end, it's probably going to be too late to maintain things as we're used to. Anyway, I said it'll take way too long. These are E. coli bacteria. Stay away from them. Found in human intestine. Stay away from them. Okay. Here is a growth rate population graph. That looks pretty benign, doesn't it? It's a pretty slow process, except that's how it keeps going. I mean, even though it's awfully slow here, it doesn't seem like it's doing too badly, but in time it just, same length of time here for it to grow that much, out here it would grow that much. Okay, so it's really gets going. So typically what happens, you can consume a little bit, and what doesn't get killed in your gut, if it starts populating, then all of a sudden, a few hours later, you're quite sick. Very, very sick. I don't know for sure if it was E. coli, but I remember my dad went to my mom's family reunion, and someone had bought, and she was a great cook, but she had just gotten sloppy in the kitchen that day, and this one chocolate pie was contaminated with something. And my dad happened to have had two pieces. It was so good. And one of my uncles had another piece. Both of them got very sick. My dad sick enough to go to the emergency room. I mean, he was in really bad shape. So yeah, it was several hours later, but they went back to that pie. Okay. Here's a theorem on exponential growth. If y is a differentiable function satisfying this kind of a differential equation, then your solution, in other words, if your derivative is a multiple of your original function, then you got this is going to be your solution. Oh, this is differential equations. I'd say that's a different course, so let's not fiddle with that too long. This represents a computer simulation of radioactive decay. It's a random process, so this is, let's not do too much of that. That's the trouble. These slideshows are really pathetic, so to speed through them sometimes. Right. It's not particularly helpful. On the other hand, you can have exponential decay. And this is very common. This would be if you got a shot of penicillin at this point, and you got this many milligrams in your bloodstream, then this is going to follow exponential decay as far as what's in your bloodstream later. And quantity of penicillin in the bloodstream decays exponentially. And I wish they had started this at 400, and then this would have made sense. This would have been what we call the half-life. Okay, that time period. If we had started at 400 and reached 200, we call that the half-life. Why they started up here doesn't really mean anything. But yeah, now that's why, and this is for any drug. My wife used to have, almost eat ibuprofen because of headaches and things like that. And what she had to do was maintain a certain level in her system. So it always does like this, and you're trying to maintain, and you take another, and you follow sort of a sawtooth pattern because it's always when you're doing. And that's why the thing is every 4 hours. Take 2 every 4 hours. That's to maintain some acceptable level in your bloodstream. I think I told y'all before I have a form of leukemia. Back when I had really harsh chemotherapy, my wife discovered I had to maintain a certain amount of composine in my system, or else I was going to throw my guts out. And she was like a hawk on it. Take your composine. I'm not feeling it. You got to get it in there, because if you wait till you feel bad, you're going to puke. Take it now. And so she was maintaining that level in the system. And that's why you take certain things every so many hours to maintain. And that's when they say you're prescribed antibiotics, you take them a certain time period to maintain that level. They say take the full dose because you want to make sure you wipe out the population of E. coli or whatever it is you're doing. So this is exponential decay. Now, this is really jumping around a lot. This is what I was talking about before when I mentioned doubling time. If you have exponential growth, then there's our formula for exponential growth. The doubling time is a time when your p is twice what this is. Okay? Twice p0. So you put 2p0 here, p0's cancel out, and 2 is equal to e to the kt. take the log of both sides, and you have log 2 is equal to kt. T is equal to log 2 divided by k. So that's how you get your doubling time. Whatever your exponential factor is, I called it a growth factor before, that determines that doubling. Okay? This is, so if you ever need it, you'll at least have seen it somewhere and say, remember that from somewhere. On the other hand, now by the way, here's a picture down here. This was a computer virus, and this was way back. I don't know if any of you remember Sapphire computer virus. I don't even remember it, so it's a pretty long time ago. These are the countries that were hit by it and damaged the most by it. Number of hosts with the Sapphire virus, and some 4855, whatever that means. Of course, everywhere that had high computer usage. Japan, Eastern China, U.S., Europe, Moscow, and some parts of Russia, a few parts of South America, South Africa, a few parts, Australia. A lot of this is outback. There aren't that many computers out there, but a lot of Africa didn't get it. Siberia, not too badly there, but Greenland hardly any. But so you see, computer viruses expand exponentially too, just like human viruses do. Okay, here's your doubling time, and it says 8.5 seconds. You're going to double from 4, your initial, that's your P0, to 8, and then you double that again to 16, double that again to 32, 64, and no time. Here's another. I should have really done this one first. And supposedly this is true. I don't know for certain it is. But the game of chess supposedly was invented by Indian mathematicians, subcontinent Asian Indians, way back. And some Maharaja or something, some ruler of this province in India loved this game of chess. He said, find the guy who invented this. I want to reward him big time. I love this game. So they went out scouring around, asking, finally landed on this Indian mathematician. And they took him into the court, big fabulous court here, and the ruler, whoever he was, said, ask anything of me, any type of reward, I'll give it to you. Okay? He said, no, just the fact that you're happy with it, that pleases me more than anything. No, ask me. He said, well, you got a chessboard? Yeah, you know what a chessboard looks like. 8 by 8, 64 little squares. He said, all I want is you'll put a single grain of wheat in the first square, and then double that every square. That's all I ask for. Well, at the end of the first row, I don't remember, you could figure it out, probably less than 100 grains of wheat. 2 to the 8. Say again? 2 to the 8. Yeah. Okay. 2 to the 64. Yes, then 2 to the 64. Before, yeah, the ruler said, look, I said ask for something important. No, this is all. So they started doing it. Like I said, very few grains of wheat at the end. Before they got halfway up the board, they would have emptied every granary in the kingdom. And before they got to the last grain, it would have been more grains of wheat that had ever grown on the planet. Okay? The guy lost his head. Okay, from being a smart aleck. Okay. Supposedly, I don't know if that part's true, but exponential growth is pretty amazing. That sounds like nothing. And in 64 squares, it would have been. He made the guy look foolish. He lost his head. All right. Going the other way, And this is Radon 222. Y'all heard of radon or not yet? Oh, it's almost
Discovered by Mary Curie.
Yeah, it's a byproduct of the decay of radon, which comes from uranium. But radon, the trouble is, it's one of the noble gases. Most of those other things are very heavy metals, and wherever they are, they pretty much stay. But when it decays to radon, it suddenly becomes a gas, which is also radioactive. Now, the good news is its half-life is just under 4 days. Okay? But the bad news is it can go quite a ways in 4 days. Okay? And so, even if it's buried fairly deeply, if there's enough porosity in the soil, it can get, say, into a basement, especially if there's cracks in the floor or foundations and things like this, and it can be in your house. You breathe radon. In general, you're going to breathe it out before, but if it just happens to be near that period, it could decay while it's in your lungs, and if it does that, then you have some pretty damaged tissue in your lungs, and your body might be able to repair that fairly quickly, but if it gets to your DNA and damages that, then suddenly you could have lung cancer. Not suddenly, very slowly, you can develop lung cancer. In fact, radon probably accounts for, after smoking, it's the number 2. Of course, smoking's here, number 2 is way down here, but it's number 2 probably, more than probably many of the other pollutants we have from radon. So you don't want radon in your house or your basement. You always have it. It's in the air everywhere, but you want it at a very low concentration. Actually, when I worked for Southern Research, we did research on radon 222 and how to keep it out of people's homes and schools and businesses and things like that.
Isn't it an alpha emitter? Is it the worst kind of radiation you can possibly get into your
Now, alpha is the mildest.
Well, that's it. It's on the outside of your
Yeah,
body.
yeah. Inside, it can do a lot of damage there too. Yes, you're absolutely right. So, yeah, your lung tissue is not very protective of alpha radiation because it's very vulnerable. So again, the half-life, it gets down to half its concentration every almost 4 days. Okay, but what's considered a safe level? Less than 4 picocuries per liter. And if you think about what a picocurie is, 10 to the minus 12?
100 trillion?
Yeah, something like that. Okay. Pretty small. Okay. Oh boy. Let's, for next time, there's your half-life formula. You get almost the same way you did the double formula. In fact, they look very, very similar. It's just, in fact, they're identical, okay? It's just the K is a negative number here rather than a positive number as you had before. What we'll do next time is start with not Match.com, but carbon dating. No. Anyway, we'll just take a quick look at that. We're not going to waste a lot or use a lot of time on this, but because there are some very practical applications of this of this kind of stuff, I want you to at least be aware of it. And we'll wrap this up and move on to chapter 6. Okay? We'll finish that pretty quickly. Any questions? All right, boy. This meeting once a week, not too bad, is it? Next week, we'll be meeting twice a week from then on, I think, till the end of the term. And I did hear, I think I mentioned to you before, there were some meetings that they wanted a team of us to go to. I had requested the Friday, Saturday in Atlanta. The vice president wanted the Monday, Tuesday down in New Orleans. He got his wish. So some Monday and Tuesday in June, I'll be out, so we're going to miss another day, but I'll try to record ahead of time so you can follow. I'll let y'all know so you can be here if you can. Yes, sir. Okay, say this one more time.
You basically just verify that I'm coming to class so they can see my money they lost.
Okay, maybe I'll do
It's
this
kinda
too.
nice to be right outside.
Oh, hey, okay, got it. Okay, I haven't looked through that. I thought this was your email address. I said, probably get that. So I just sent this to that you've been coming to class. Okay. I'll try to do that. When do they need it? Is tomorrow okay? Okay. Yes, sir. No, that's just
So
for the
if I
practice.
work out my book at home.
Oh, absolutely, yeah, absolutely.
Because I have a book, it's just not the same.
Not the same, but I bet you it covers the same material, right? Uh-huh.
I don't know if you have a schedule of like when the tests are going to be or something like that, but
Yeah.
I have a family trip that was scheduled, and I have a flight that comes back on June the 10th, I think, which is going to interfere with that class that week, that Monday.
Right.
So I was just wondering if there would possibility.
They're going to be take-home tests.
Okay.
You can get them when you get back.
Okay.
Or if you let me know ahead of time, I'll give it to you before.
Right. I just want to make sure there wasn't going to be some disastrous interference.
No. We'll manage. Summers are like that, you know.